chapter 7 of our lecture note discussion. What we will be looking at in this chapter is to discuss sampling distributions. And so we're going to go through the whole process of selecting a sample, finding the point estimate of a sample, which in other words is the average, and then using the point estimate in what we call statistical inference. So with regards to sampling distribution, we will look at situations where we have the sample mean, situations where we have the sample proportion, and some other sampling methods. See, the interesting thing is in statistics, our main goal is to know everything about the population. And so there are certain terms that we need to understand. An element in statistics is basically an entity on which data is collected. So when we talk about an element, we are looking at individuals. It could be people. And when they are people, we refer to them as participants. It could be animals, which we refer to as subjects. Or if it is non-living things like cars, clothes, shoes, or other stuff that are considered to be non-living, we call them experimental units. And so our goal is to know everything about the population of that element, right? And we define a population as a collection of all the individuals of interest. And so we could be interested in learning about the income levels of everybody in Prince George. We could be interested in learning about the average, the height of everybody in a specific location. And so when we consider every individual, that constitutes the population. Now, when we choose a number of people from the population and study that small group, we call that small group the sample. And so we define a sample as a subset of the population, right? And so the population is everybody, but when we take some people out of the population, we create a sample out of that. By the time we complete our discussion on this chapter, we will be looking at what we call different methods of sample selection. And then we have sampled population, which is the population from which the sample is drawn. So let me give you an example. Let's say I want to learn more about the number of hours students at CNC sleep every night. The entire population of CNC students is the sampled population, the population of interest. Now, if I take a sample out of that population, that becomes my sample. And then we have a frame, which is the list of all the elements that a sample will be selected from. But using proper sampling method, we are able to come up with good estimate about the characteristics of the population. And so this is the whole process. In statistics, even though our goal is to know the average of the population, we don't ask everybody in the population. And the reason we don't do that is because sometimes we may have some time constraint, or it could be due to lack of human resources that could help us do that. And so unless you have a lot of resources like Statistics Canada, we don't ask everybody in the population. What we do is we take a sample out of the population, we collect our data on the sample, we calculate a statistic like the average of the sample, and once we know that statistic of the sample, we will use statistical inference to generalize for the entire population. So let me give you another example. Let's say we want to know the average weight of everybody living in Prince George. Now, Prince George has a total population of about more than, I think, 100,000. And so talking to 100,000 is kind of a difficult task to perform. So what we will do in statistics, even though we want to know the average weight of everybody in Prince George, what we will do is we will take a sample of individuals from Prince George, and it could be a random sampling, right? We look at different methods of sampling selection. But we could take a random sample of everybody living in Prince George. From the sample, we will collect their weight. So maybe we could take, instead of 100,000, we could take a sample of maybe like 100 people. And then we will collect their weight. calculate the sample average or the sample weight for the 100 people, and that will give us a number, right? So maybe the sample weight is, let me say 110, right? So we calculate a sample weight of 110. Right? And then what we do is we will use statistical inference to generalize for the entire population based on our sample weight of 110. And so we have what we call a sampling distribution of the sample mean. When we take multiple samples out of the population, we can calculate what we call the mean of the sample mean. What I'm trying to say is, consider this is the entire population. And then I will take 3 samples. So the first sample, the second sample, and then the third sample. Now make sure all these samples are of the same size. And so maybe 100 individuals here, another 100 here, and another 100 here. So 3 samples of the same size. Now what I'll do is I'll find the average, which is the X bar 1 of the first sample, find the average, which is the X bar 2 of the second sample, and then I'll find the average of the third sample. What we're saying is studies have proven that when I take these 3 averages of the 3 samples and I find the average of these averages, it will give me what we call the mean of the sample mean. More or less the average of the sample averages. And we know that the average of the sample averages is always equal to the population average. And therefore, the average of sample averages could be our unbiased estimator of the population average. And so notice, very important for your midterms, the average of the sample average, which is mu x bar, is the unbiased estimator of the population average. Means is equal to the population average. Now, it's the same thing with the standard error. When it comes to finding the standard deviation of the population, sometimes it's difficult because we cannot study everybody in the population. It becomes a little difficult. And so, depending on whether the population is considered to be finite or an infinite population, our standard error is calculated using this formula for an infinite population or this formula for a finite population. Now, somebody will say, how do you know the population is finite or infinite? By using this rule here. So let's say I have a population of 1,000 people. That's a population size. We represent it as big N. And out of this population of 1,000 individuals, I choose a small sample of 100. Now, the big question is this a finite or an infinite population? To determine whether the population is considered to be finite, we use this formula here. The formula says divide your sample size, and so my sample size is 100 by your population size. My population size is 1,000. Now, if your sample size divided by the population size is less than 0.05, the population is considered to be finite, and this is how we'll calculate the standard deviation of the sample mean. If it is greater than 0.05, we consider the population to be infinite, and this is how we find the standard deviation of the sample mean. When I divide 100 by 1,000, I get 0.1. 0.1 is greater than 0.05, and therefore this population here will be considered as an infinite population, and the standard deviation of the sample mean will be calculated using that formula here. Now, it's important to note that in this course, we will be dealing with infinite populations a lot. And so get yourself ready for that. So knowing these two very important parameters, I want to introduce you to what we call the central limit theorem. The central limit theorem is basically saying that when you have any distribution, and the distribution does not have or does not follow the normal curve, right? And so it could be any distribution. It could be a binomial distribution. It could be a Poisson distribution. It could be an exponential distribution. There are so many distributions out there. So when we are not able to describe the shape of this distribution, we can use the central limit theorem to approximate whatever the distribution is as a normal distribution. Now, we already know from chapter 6 that normal distribution follow the bell curve, right? And so maybe it's a binomial distribution or a Poisson or exponential distribution. We are not able to determine the shape of that distribution. Using this theorem, we can assume or approximate that distribution as a normal distribution. Now, in this course, when it comes to central limit theorem, we are only going to look at how we can approximate a binomial distribution as a normal distribution using the central limit theorem. And so that's the only time we will be using the central limit theorem, when we have to approximate a binomial distribution as a normal distribution. Okay, but let's go over how we use this. This at this point is just a theorem, right? But let's learn how we can actually apply the central limit theorem. So let's take a look. In a case like this example here, what is the accumulated probability that a simple random sample of 30 applicants will provide an estimate of the population mean SAT score within 87 standard deviation? Okay, so that's a very important point. Of the actual population mean of 1,697 if the sample mean is 1707. Now, we are not so sure what kind of distribution the SAT scores follows, but what we are trying to do is we want to find the probability that a simple random sample of 30 applicants will provide an estimate of the population SAT score when we know the standard deviation to be 87 with a mean of 1,697 as the population mean if the sample mean is 1707. Now, when we read a question like this and want to apply the central limit theorem, okay, remember the central limit theorem says that the sample mean will be approximately normal for a distribution with a population mean and the population standard deviation divided by the square root of the sample size. So when we know the population standard deviation and we also have the sample size and the population mean, we should be able to approximate whatever the distribution is as a normal distribution. 4 very important parameters here. Number 1, our sample size has been given to us, and according to the question, our sample size is 30. The other thing we know is the population standard deviation has also been given to us, and we have a population standard deviation of 87. The population mean, according to the question, is a SAT score of 1697, which is the population mean, and we know the sample mean is also right here. Our sample mean is 1,707. For the purpose of your final exams, it's important to know how to apply the central limit theorem. How do we do it? Step 1, we will standardize the distribution just like we did for Z distribution. If you still remember, for normal distribution in chapter 6 discussion, remember we learned how to standardize it to find the Z value. It's the exact same thing. We use this formula here where we subtract the mean of the population from the standard deviation divided by the from the sample mean divided by the standard deviation over the square root of n. Our population mean from here is 1,697. We subtracted from the sample mean of 1707, and then we divide it by the standard deviation over the square root of our sample size. This will give us a standardized value of 0.63. So when we approximate this distribution as a normal distribution, our standardized value z is 0.63. The next thing we're gonna do is we're gonna go over to our standard normal distribution table, and then we're gonna find the probability, the cumulative probability. So just like we did for normal distribution, we take our standard normal distribution table. For those of you who don't remember, when we go on model and you look at chapter 6, we still have our standard normal probability table. So this is the table we will be using for this exercise, right? But let's go back to the discussion here. So our standardized value was 0.63. On the table, we are going to look at 0.6 on the side, and then the 3 over here. Where these two values intersect, so we have our 0.03, and then we have 0.6 right over there. Where these two meet, that is the probability or the cumulative probability of 0.63, which is 0.73565, right? But when you round it off, you get 0.7357. So this is the cumulative probability, which means when we approximate the distribution as a normal distribution, this will be our cumulative probability that the SAT score average will be less than 1,707, which was the sample average given to us. For those of you with a TI-83 calculator, you can follow these steps. But I'm going to leave this practice question here. When we meet for our discussion, sometime on Monday, we will be, and Tuesday as well, we will be looking at this practice question. Now, the exact same principle applies when we're dealing with proportional distributions. See, we said we apply the central limit theorem when we have binomial distribution, which is the exact same thing as proportional distribution in this course. We want to know what proportion of the population favors a certain cause, or what is the population proportion of success. We don't ask everybody in the population. First, we take a sample, we calculate our sample proportion, and then we use statistical inference to estimate what the population proportion will be. With proportional distributions, we are looking at categorical variables, and we are limiting ourselves to proportional distributions where we possibly have only two outcomes. So let's take, for example, a situation where we want to know what proportion of UNBC students enjoy living on campus. So we have two different options. Those who love to live on campus, those who hate to live on campus. Our proportion of the entire population that we are interested in is what percentage or what proportion enjoy living on campus. We cannot ask everybody at CNC, right? Because that's a very tough task. So what we do, we select a sample of students. So maybe out of the 5,000 students at CNC, we take maybe 500 students. We'll ask the 500 students, how many of them enjoy living on campus? We will know that proportion. We will use statistical inference to estimate for the population. So just like we did for other distributions that are considered to be quantitative, here we're going to look at distributions that are considered to be qualitative. Let's look at how it works. Our infinite population standard deviation that we will be using is this formula here, just like we did for the infinite population in a case of quantitative variables. For the qualitative variables, this will be our formula for the standard deviation of the sample proportion and our mean of the sample proportion will be done. So applying the central limit theorem therefore means that our qualitative variable sample proportion will be approximately normal using the central limit theorem at the population average divided by the standard deviation of the sample proportion, which is p minus 1 minus p, all divided by the sample size n. So this is how we're going to apply the central limit theorem. The first one we did was for when we have a distribution that is considered to be quantitative. In this case, we're looking at how do we apply the central limit theorem in a distribution considered to be qualitative or categorical. Now, to be able to do that, the first thing you need to know is to make sure that these two conditions are met. To be able to approximate the proportional distribution as a normal distribution, these two conditions must be met. The sample size times the proportion of success should be greater than 5, and the sample size times 1 minus the proportion of success should also be greater than 5. When these conditions are satisfied, the probability distribution will be approximated as a normal distribution and not as a binomial distribution. Let's take a look at an example and see how this works out. If 72% of the prospective students applying to St. Andrews College desire on-campus housing, what is the probability that a simple random sample of 30 applicants will provide an estimate of the population proportion of applicants desiring on-campus housing that is below 77% of the actual population proportion? So here we know three things. We know the proportion of the entire population that we hope applying to the university or the college will desire on-campus housing, 0.72. When we take a random sample of a specific site, say 30, we want to know the probability that out of this 30 sample size, 77 of them, or 77%, which is 0.77%, will actually desire on-campus housing. So we have the population proportion of 0.72, our sample size of 30. We want to know the probability that 0.77 less than 0.77 will desire on-campus housing. This tells us we are dealing with a binomial distribution. But to be able to apply the central limit theorem, these two conditions must be met. The first condition is that when we multiply the sample size n, which is 30, by the population proportion of success, which is 0.72, it should be greater than 5. When we multiply these two, we get 21.6, which is greater than 5. The other condition is that our multiplication of the sample size and 1 minus the proportion of success should also be greater than 5. Our sample size is 30. 1 minus the proportion of success, which is 1 minus 0.72, is 0.28. When we multiply these two, we get 8.4, which is also greater than 5. So because this condition is met and that condition is met, we can use the normal approximation method to find the probability for this binomial distribution here. So step one, just like we will standardize just like we standardize the quantitative case, we will standardize in this case as well. But our standardization formula for this qualitative variable is different, right? Because here we're dealing with proportions and not averages. So we take the sample proportion of 0.7277 minus the population proportion of 0.72 divided by the standard deviation of the sample proportion, which I did here, and that gave me 0.08. So remember, the standard deviation of the proportion formula is 1 minus p into bracket 1 minus p over n all squared root. So we did that calculation here to get our standard deviation of the sample proportion, which is 0.082, and that is what we have right here. When we standardize using this formula, we get a z-value of 0.61. This here is our standardized z-value. After finding the standardized z-value, we go on to the next step where we calculate the probability using the standard normal probability table. We go on to our standard normal probability table. You can always download it from Moodle, or you can also Google it, but we're going to find the lower tail probability of 0.6. So 0.61 will be right here. And so the lower tail probability, or the probability of those below 0.61 is 0.72907. So when we come back here to our calculation, we find the area under the curve to the left of 0.61, which is 0.7291. Remember, we take the first digit after the point on this side, we take the second digit after the point on that side, and where these two meet, the intersection becomes our probability. So the probability that somebody 0.77% of the sample will prefer or desire on-campus housing is 0.7291, which means there's a 0.7291% chance that 77% of the students will actually desire on-campus housing. Okay, I have a quick practice question on that here for you. We will discuss this practice question when we meet for our lecture discussion on Monday. Okay, last aspect I want to talk about before we complete our discussion on chapter 7 is how do you choose a sample? Data sampling is a very important thing to do in statistics because your method of data sampling determines whether your data or your results or conclusion will be biased or not biased. The first method after simple random sampling is stratified random sampling. Stratified random sampling is a very simple method. What we do in our selection is we take the entire population and then we divide the population into groups called strata. And so we can have two groups. It doesn't always have to be two groups. You can have 3 or 4, whichever one you desire, right? But the simplest version is to divide them into stratas of 2 groups. And then we choose from, say, this is group A, and here we have group B. And so out of these 2 groups, we will select a random sample from this group, another random sample from this group. Together, we create our sample from there. So let's take, for example, I want to choose out of a population of 100 students, I want to select my sample using a stratified random sample. First thing I gotta do is I gotta create them into 2 groups in the simplest form. Now it doesn't always have to be 2, you can get more than 2 groups. But maybe I divide a class into 2 groups. The first group will be those who are wearing glasses, and maybe those that are wearing glasses were 60 of the 100 students in class. Then the second group will be those that are not wearing glasses, right? And you can use different ways to divide them into groups. You can use gender, you can use height, you can use age, right? But in this case, I'm just using glasses. Group A are those wearing glasses. Group B are those not wearing glasses. And so if 100 students, 60 of them are wearing glasses, that means 40 of them are not wearing glasses. Now the next thing I'm going to do is I will take equal number from this group, equal number from that group. So maybe I'll take 5 students from those wearing glasses randomly, And I also choose randomly another 5 students from those that are not wearing glasses. And so together, I have 5 from the A group, the glasses group, 5 from the not glasses group. So then I create a random sample of 10 students with 5 of them wearing glasses, 5 of them not wearing glasses to form my random sample. Now, when we select from this group, we do that randomly. So it's not based on favoritism or based on any specific characteristic. It's just a random selection from this group. And that's why we call it stratified random selection. First, we create them into groups called strata. And then the second step, we randomly choose from each group to create a sample. Now, another one which is very similar to stratified random sampling is the cluster sampling. Very similar in the sense that we divide them into separate groups called cluster as well. And then each cluster will represent a small scale version of the sample, and then we'll randomly choose from the cluster. The difference though with cluster sampling, we divide them based on proximity. And so let's say I want to perform a sampling selection in Prince George population, and I want to use the cluster sampling, right? What I would do is I would divide my population into groups called strata based on the proximity. So those living on College Heights will be one cluster. Those living by Foothills will be another cluster. Those living downtown Prince George will be another cluster. Those living by Costco will be another cluster. Those living on the Heart will be another cluster. So then I have about 5 or 6 clusters, and I'll randomly choose from all of these clusters to form my sample. So cluster sampling, it looks a bit similar to stratified. The difference is proximity of the element is what we use to divide. Now, another example of sampling selection I want to also talk about is a systematic sampling selection. Here, we take the entire population, we divide the population by our number of desired sample size, and every person who occupies that number becomes part of our sample. And so let's say we have a population of 1,000 students, and I want a sample of, say, 10 students. I would divide a population of 1,000 by 10. And so the 100th person on each count becomes a member of my sample. Right? Now, this is easy to perform. And the interesting thing about this sampling selection is that it's random because you don't know who is going to occupy the 100th position on every count. Now, we also have convenience sampling, which is known to be a non-probability sampling technique. Here, our selection is based on convenience. Who is it conveniently possible to add to a sample? And so a professor conducting a research on students out of convenience wouldn't have to leave the college and go to a different province and work with students there, but might want to use students that are very close to him at, say, the college. A person who wants to perform a research at a supermarket wouldn't have to leave and go downtown and ask somebody there. Using convenience sampling, he can just ask those that are conveniently available to him. And that is why we consider it not to be a probability sampling technique. The last one I want to talk about is judgment sampling. Here, we select our sample or our participants using our own judgment. Judgment sampling is also another example of a non-probability sampling technique. We choose our samples based on our opinion or who we feel will be more representative of the population. And so it's an easy way to select a sample because you don't have to go through the process of randomly choosing or dividing them into cluster or strata, but it's a non-probability method of sampling and it's not recommended. So what will be my recommendation if you have to perform sampling selection? I will always recommend that number one, you could use simple random sample, stratified, cluster, or systematic sampling. It's always advisable to use a probability method of sampling as opposed to a non-probability method of sampling. The non-probability method of sampling are mostly based on convenience and judgment or personal opinions, and therefore may not be representative of the entire population. Okay, I'm gonna end our discussion here. This is a very short chapter to discuss, but I'll see you in class and we will do the further discussion on this on Monday. Thank you and see you in the next lecture discussion.